Okay, let's start. So I forgot to bring two things. One is the laptop chargers, one is the microphone. So I don't have microphone today. So but does anyone have a laptop charger that have the round head and borrow me? Because I'm not sure my laptop can last for 2 hours. You guys have laptop charger? No. Maybe later someone can borrow me your laptop or not to continue the recording, huh? Sorry. Windows. Yeah. Go ahead. Yeah, Dell. Mm, yeah. Okay. So let's start. Anyone try the question I gave you last time? Show that t plus t squared minus 1. Okay, so first of all, you look at the ring of ct quotient by t squared minus 1. Okay, and then look at these ideals here. Does anyone trying to work out this example or not? Okay, let's recall what is this. So we want to look at the ideals of the quotient ring. Ct over t squared minus 1. So this is a polynomial ring, okay, in one variable t over the coefficient ring c, portion by the ideal generated by t squared minus 1. Does everyone know what this have uh have any question on what I said just now? Ideal generated. So maybe just to test you, what are the elements in the ideal generated by t squared minus 1? What are the elements here? This is a principal ideal generated by t squared minus 1. Okay, so these are all the multiples of t squared minus 1, where these m's are the elements in your ring. Okay, so what are in here? What are the things in here? For example, what is in this set? Chris? What are the things in this set? What kind of m you can take? Sorry? In what? The integer. Why? Or you mean the m is the integer? Okay, so what are the choice of elements here? If you take integers, multiply t squared minus 1. Huh? 2? How do you get? So, how do you write m times t squared minus 1 equals to 2? For some m in CT. Can you do that or not? Can you do that? No, right? Okay. Unless t squared minus 1 is invertible. Right. So what other choices of m you can pick here? Factor of t squared minus 1, for example. 1. Okay. So So you could have t squared minus 1 here, right? And then you can have t minus 1 times t squared minus 1, t plus 1 times t squared minus 1, right? Because t minus 1, t plus 1 are the elements in your polynomial ring. Okay, does it make sense? Okay. Okay, so these are the things in your ideal. Okay, so how to understand this quotient ring here, ideals of this quotient ring. So last time we learned about the correspondence theorem. Okay, what does the correspondence theorems in quotient ring say? So let me put correspondence theorem. So you have a surjective homomorphism, okay, from R to R prime, surjective ring homomorphism. Okay, similar to the correspondence theorem in subgroup, right? So what does correspondence theorem in subgroup says in groups? If you are given a surjective group homomorphism, then every subgroup in the codomain groups, you can have a bijective correspondent to the subgroup that contains the kernel of the homomorphism in the domain. Correct or not? Okay. So here is the same. So you take any ideal inside your codomain. Okay. There's a one-to-one correspondent to the ideal in your domain that contains the kernel of your ring homomorphism. Okay, it's the same. It's the bijective correspondence. Okay, so here is the bijective correspondence. Okay, no? Okay. So just now we have this CT over the ideal generated by t squared minus 1. How do we study the ideals in this group? We can use the surjective ring homomorphism. Okay, what's the surjective map we can study? So we can consider a surjective homomorphism from CT to CT quotient by t squared minus 1. How to build this surjective map here? How to build this surjective map? Alright. So I just send any element to it coset. Okay. I just send any element to the coset. What is this? This is the canonical map. Okay, so this is the canonical map. What does this mean here? What does canonical map means here? For example, the uh, look at the element t squared minus 1. Where should this polynomial go? Under this map. What's the representative of coset that t squared minus 1 live in? So inside the quotient ring, okay, what is equivalent to the identity? What is equivalent to the identity? The identity coset is what? Huh? Sorry? Ideal of t squared generated by t squared minus 1. Right. So meaning t squared minus 1 is inside this ideal, right? So it is in the identity coset. Okay. So this is get sense to the uh, identity coset, which is the ideal generated by t squared minus 1. Okay. Okay or not? Okay. For example, next example, maybe t plus t squared minus 1. Where should this elements go under this map here? It should go to t bar. Yeah, no? T bar, which is equals to t plus t squared minus 1. Okay. 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 So this is the canonical map. So you send every element to its representative. So in this case here, what's the kernel of phi here? What's the thing get sent to the identity coset, which is the principal ideal generated by t squared minus 1. Okay. 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 So in this case here, we have the surjective map. Okay, we have the surjective map because all the coset here, okay, we can pick the representative as the pre-image. Okay. So let me write it down here. So for all the a plus t squared minus 1 bar, you can pick a, okay, to be the pre-image. Okay, no? So not that when I write a coset here, right? This is an additive coset, right? Okay. So this is the additive coset here. Okay. We are considering the additive coset, not multiplicative. Uh, it's multiplicative coset partition your ring, right? Is it possible? Because our multiplication doesn't form a group, right? So inverse might not exist. But you can talk about field, right? Talk about field where the multiplicative is invertible, but still 0 is not invertible, right? Yeah, 0 is not invertible. Yeah, there's always one thing that's not invertible. So it might not form a group under the quotient. Okay. Okay. Yeah. So that's why we consider additive inverse here. Because you need to consider an plus bn, right? How to get back to n? How to get back to the identity? But additive, your ring is always an additive group, abelian group some more. Okay. Then your inverse exists. Okay. So how to get from an plus bn to n? You just take a inverse n, right? Or b. Okay or not? Yeah. Okay. So we want to study all the ideals on the right hand side. Okay. But we have this surjective map, right? So we can use the correspondence theorems to study all the ideals in CT that contains the kernel. But what is CT here? This is a polynomial ring over a field. What did we mention about polynomial ring over a field? We can always use the division with remainder to reduce every ideals so that the ideals is generated by one unique monic polynomial of the lowest degree you can find in the ideal. Okay. So by correspondence theorem, every ideal in the quotient ring is in bijective correspondence with the ideal in CT. What kind of ideals in here? This ideal must contain the kernel of the map. Okay, kernel of must contain the kernel of phi. Okay. Okay. But CT is a polynomial ring. Okay. In with one variable over field over the field C. Okay. So we know that every ideal in a CT is a principal ideal. Okay or not? Okay. Why is it a principal ideal? Because it can be generated by a unique monic polynomial of the lowest degree you can find in the ideal. Okay or not? Okay, remember division with remainder, we can always divide, do division. Remember the argument with the remainder, and then we show that the remainder must be 0. Okay, otherwise it will contradict the choice of the lowest degree polynomial. Again, remember the proof, recall the proof. That proof is a very important proof. Okay, so we know that every ideal in CT is a principal ideal. But for ideals containing kernel phi, okay, for the ideal generated containing kernel phi, So for I equals to sum F in CT containing a kernel phi here. Okay, we must have F. Okay, dividing what is in the kernel phi. Okay, what's in our kernel phi just now? What is in our kernel phi? Is the multiple of t squared minus 1. So since this thing is inside, okay, it's inside our ideal, right? So, but my ideal only generated by one element. Then this generator here must divide t squared minus 1. Okay. Okay. I guess some of you will confuse here. So please ask if you are confused here. The reason I think you are confused is because I put different concepts together. Maybe you don't know why these concepts are linked. But maybe people lost by various reasons. So you should ask if you are not following now. Okay? So I repeat again. So my I that I consider in the corresponding theorems here contains the kernel phi, okay, generated by t squared minus 1. But just now I argue that the ideal I consider here must also generated by only one element. So this one element here will help you generate t squared minus 1. So this means t squared minus 1 must be a multiple of f. Okay. Okay. So this means what? You really don't have much choice here. Okay, how do you divide t squared minus 1? So this means f has to be 1, t plus 1, t minus 1, or t squared minus 1. Okay? Yeah. Okay. So these are the only possible four ideals that contains t squared minus 1. Okay, so let me write down here from the from correspondence theorems. Correspondence theorems. So we have CT and then an injective map into CT over t squared minus 1. So always remember what's this map here? This is the canonical map. So you just send every polynomial across and then kill all the multiple of t squared minus 1. Okay, you kill all the multiple of t squared minus 1. So you have ideal generated by 1 here, t squared, t plus 1 here, t minus 1 here, and then t squared minus 1 here. Right, so these are the ideals here. And then all these ideals will contain the kernel, which is the ideal generated by t squared minus 1. Okay. So correspondence theorems tells you that these are the only ideals in the domain. And then they are in bijective correspondent with the ideals in the codomain. Okay. So if I want to study the ideal inside the quotient ring, I just map all this element across. Okay, I just map this all this ideal across. Okay, make sense? Okay, so what's the image of this ideal here? Yes, is it coset or not? Last time I say that uh it is a coset, right? Actually, it is not. Why? Why? Actually, why? So, for example, okay, let's talk about group first. Is a subgroup equivalent to coset or not? What's the difference between subgroup and a coset of subgroup? Coset can partition your group, but any other property? Yeah, coset might not contain identity. So coset might not be a subgroup. But the argument here is I will send ideals to ideals. Okay, I will send ideals to ideals. Okay, I'll send ideals to ideals. So what's the image of one in this case here? So the image of one here is really just the codomain, right? Let me think. Wait, what's the image of one here? Yeah, sorry. So why the element is and only is ideal not consent. Oh, okay. Okay, right. Okay, so this is about the proof of correspondence theorem. So it's like image of a subgroup under group homomorphism is a subgroup. So ideal is the same. So image of an ideal is an ideal. Pre-image of an ideal is also an ideal. That's the map we use in the correspondence theorem. Okay, so ring homomorphism will send ideals to ideal, subgroup to subgroup. Okay. Hmm. It's quite different from the no, no. Subgroup also sends. Remember the assignment question the S S4 S4 to S3 map. Yeah. Yeah. The S4 to S3 map. So you start by finding the 6 subgroup in S3, right? And then you look at the inverse image. Okay, it's the same, it's the same. But here we have extra structure, which is ideal. Okay or not? You can try and show. You can try and show. Image of an ideal is still an ideal. Okay, pre-image of an ideal is also an ideal. You can try and show this. Okay. Yeah. So what's the image of one here? So last time I just wrote 1 plus the ideal divided by t squared minus 1, right? This is not quite accurate. Actually, it is an ideal generated by this thing. Okay, it's an ideal generated. So I need to put another bracket again to talk about ideal. Okay, what is this thing? Actually, this is the whole ring, whole quotient ring. Okay, because the unique ideal is what? The unique ideals is exactly your ring. Okay, the unique ideal is exactly your ring. So similarly, you send the ideal t squared plus 1 to the ideal generated by t squared plus 1 plus the ideal generated by t squared minus 1. Like this. And so on. So last time I forget to put a bracket on the outside. This is just this. Okay. So maybe I think if I just put like this, this is the same as this one. Yeah. If I use all the multiple to generate, I should get the same idea. Okay or not? So actually, 4 of these are ideal. But last time I asked about one question whether they form a coset or not. Right? Actually, they don't form the coset because the image that ideal give you should be an ideal. I was also having a hard time, so I'm not sure if you try it out or not. So if I just look at the coset, one plus t squared minus one and t minus one plus t squared minus one. Okay. Try and add them together. I get t plus t squared minus 1. And then I ask whether this coset is equals to one of the 4 coset that is 1 plus t squared minus 1, t minus 1 plus t squared minus 1, and then t plus 1 plus t squared minus 1, and the ideal generated by t squared minus 1. Right? Whether this t plus t squared minus 1 is either one of these 4. Actually, t plus t squared minus 1 is a new coset. You cannot generate using the other 4 coset here. Okay, they are belong to different equivalents. No, they are belongs to different coset. Okay, yeah. Which one? Which one? Which one? Okay, so here, please differentiate. Here on the corresponding theorems here are ideal. Okay, but if I don't generate it, I can form the additive coset. You see, there's no bracket here. Make sense or not? So you can see that what's the difference? What's the main difference here? So 0, let me think. Yeah, 0, for example, is in the ideal generated by 1 plus t squared minus 1. But 0 is not in the coset of 1 plus t squared minus 1. Can you see this? Can you differentiate between coset and ideals or not? I think this one is the main confusion for this part. Ideal of coset or ideal generated by the coset. Yes. Yeah. Yes. Yeah. Correct. Yeah. Yeah. Last time I just write it as coset. So it was wrong last time. So I need to put an extra bracket here. Yeah, no. Because under ring homomorphism, ideal send to ideal. Yeah, ideal send to ideal. Okay. Okay or not? So the answer for last time is you get a new coset. Actually, I think there are infinitely many coset for this ideal. Yeah. I go back and think about whether this t plus t squared minus 1 is one of these ideal or not. So spend quite a long time and then only figure out that This 4 coset here doesn't partition the ring. Okay, so doesn't partition the quotient ring. Okay. Does it make sense? Okay or not? Okay. Any question about this example here? No? Symbol shaking head means got question or no question? Okay. I think I finished this question. I feel like maybe only 10% of you understand everything what I say. But the rest, I can feel that you don't understand, but I don't know exactly how to address your question. I mean, when I explain, I'll try as much as I can, but something that I don't know, I'm not sure how to handle it. So please just let me know your need. Okay, just let me know your need. What's your problem? What's your question? Then I will try and put this info into it. Because when you ask me question, right, I will learn your perspective. Okay, I will learn your perspective. And then I will see the question in your perspective. And then I will try and think what's the problem you might make. Okay or not? So that's why when you ask question, it's very important. I will see from your perspective. Is it okay? Because sometimes I learn things also using my own way to learn. Of course, you learn things also using your own way to learn, right? So make sure you can talk to me, and then I can try and figure out uh what's your concern. Okay, and then I will help you to settle it. Is it okay or not? I mean, I need to have at least one representative to from each level. So for example, I can partition you guys into different level. Some very good, some mediocre, some weak. So I need to have at least one representative from one of this group to ask question. Then I can settle the problem for this group, weak group, or mediocre group, or the pro group. Okay or not? You cannot just have pro asking question because mediocre student or weak student don't get it. So mediocre and weak student should also ask question. And then once you ask it, just one representative is enough. Then other with the similar thinking, they will get the idea also. Okay or not? So the most important thing is you must talk. You must talk. Okay, you must talk in this class. Understand or not? Because I keep like spending time like this, right? It's kind of a waste time if you don't appreciate it, okay, or if you don't take it seriously. But if I do like this, but you learn something, then that would be good. Okay or not? Because I can opt to just let you study yourself. I just say one time and then you go and do yourself. I can. But I choose to come back and talk again, come back and talk again, come back and talk again sometimes, right? So make sure you take this opportunity to ask. Well, why the first time I don't understand it? I don't get it. And then what's the issue I met, for example? Like the issue I met last time is I ignore the fact that it is the image of an ideal is an ideal. So this is the main point you have to get today. One of the main point. Okay. If you look at the image of an ideal, you must get an ideal. Again, not just a coset. And then this example is kind of confusing because you are looking at the quotient ring. Okay, ideal in the quotient ring. So inside here, the ideals are generated by the representative, for example. Okay, so make it a more complex thing to write. Okay or not? Yeah. Yes. Zhe. What do you mean? Which coset? The bottom one? What's the use of this coset? It's the same as the quotient ring. What's the use of the coset in quotient rings? Sorry, quotient group. Isomorphic. Isomorphic. You mean first isomorphism theorem? So the coset in the quotient group form a group. That's why we call quotient group. Right. You have a group, you take a normal subgroup, okay, and then you quotient it. You get another group, which we call the quotient group. Okay, G mod n. What is the element in quotient group? These are the coset. Similar with rings here. We have rings. Instead of normal subgroup, we have ideals. Because exactly this is the property that a kernel of a homomorphism have. Right. Kernel of a group homomorphism form a subgroup. Kernel of a ring homomorphism form a ideal. Okay, so you can take your ring, quotient out by your ideal. And then you have these coset, additive coset here. And then this additive coset will form a ring. Okay, so to form a ring, I need to tell you how I add and how I multiply. Two law of composition. Okay, how I add A plus I plus B plus I. How to add? I get A plus B plus I. Okay, A plus I times B plus I. What do I get? I define it to be AB plus I. Okay, but when you multiply two ideal, you don't always get ideal. This is your assignment question. Okay, when you multiply two ideal, I times J, it is not always an ideal. Okay, so you need to make it an ideal. Okay, you need to make it an ideal. Okay. Yeah. Yeah, the definition is intuitive, but you need to show why it works. Okay or not? So that's why you need to prove it. Sorry? Yes, 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 yes. Ideals are more important than subring because ideals are the kernel of some homomorphism. It's just like normal subgroup. It's a kernel of some homomorphism. Okay or not? Any question? Any question? Any question? No? Yes? The difference. Okay, good. Very good. So one difference I show you is you can see that. Okay, so let me. Okay, very good. So okay, actually I show you one of the difference already. So let's look at the ideals and coset here. Okay, So for example, coset, I can take 1 plus the ideal generated by t squared minus 1. Okay. And then I can make this into an ideal like this. Okay. Of course, when you talk about these ideal and coset, right, you need to talk about which ring you live in what ring, because you need to know multiple of what. Okay, where you can take the multiple from. So our ring here is CT over t squared minus 1. Okay. Okay. So what is inside the coset of 1 plus t squared minus 1? So here we have 1, element 1, because inside the ideal generated by t squared minus 1, you have 0. I can take 0 times t squared minus 1. Right. So 1 is in there. What else is in there? 1 plus t squared minus 1, which is t squared. Okay, t squared is in this coset here. Okay. What else is in here? 1 plus, for example, t minus 1 times t squared minus 1. This polynomial is in here. Okay. Makes sense? Okay. But in ideal, what happened? In ideal, what happened? We also have these guys in here. So those in the right, yes, right-hand side is always in the left-hand side. Why? Because I can realize them as 1 times the element. And 1 is in the ring. Okay. But the ideal generated by 1 plus the ideal t squared minus 1 has more things. What else do I have? I have 0 times t squared, for example. Okay, equals to 0. Because t squared is in my ideal. I can take 0 times t squared. So 0, in particular, 0 is in this ideal here. Okay, but 0 is not in the coset of 1 plus t squared minus 1. You cannot find 0 inside this coset. Can you have 2 in ideal or coset? Both. Yeah, can you have 2? It's a very good question. I think you don't have in both. Where is 2? Okay, before that, first of all, is Pishon happy about these elements? Where I get 0? So where is 0? So this is the 0. This is the 0 in CT over t squared minus 1. Yeah. So this is the 0 in here. What are the zeros in here? Actually, this is very interesting. What are the 0 in here? This is not just 0, you know. This is the coset of 0. A bit confusing. But to be precise, right? To be precise, I need to write bar on the top. Because why? Because my elements is in the quotient ring. So what's the element in quotient ring? These are the coset. Okay or not? But I'm okay to write 0 here. Because if I multiply t squared with, for example, let's look at this guy. So let's look at t squared minus 1 times t squared. Okay. What is this? This is a multiple of t squared minus 1. So this guy should be 0 inside the quotient ring. Or I would say that they have the same representative. Okay, or I just put the whole bar here. When I do this bar thing, right, you should think of Z mod and Z. How you multiply things inside Z mod and Z. How you multiply A bar with B bar. A bar times B bar is just A times B bar. You need to remember, recall the Z mod and Z. You need to have a prototype inside your mind when we talk about quotient ring. Quotient group. Okay, you need to have a Z mod and Z as your prototype. How you multiply inside there, how you add them inside there. You need to understand fully that example first. Only you can imagine how we do operation inside here. Can or not? So if you don't understand what I said, the first thing you go back, you should do is go and write out the operation in Z mod and Z. How you add there, how you multiply there. Write it out. How you do coset addition, how you do coset multiplication there. Okay. But as you can see here, 0 is inside my ring. What are the 0 inside the quotient ring? This is the what is this actually? What is this 0 bar here? What is this 0 bar? So this 0 bar is just the ideal generated by t squared minus 1. Okay. Yeah, Ishan. Okay. Yeah. So another question is from the Qian, right? So it's 2 inside the coset or in the ideal or not? So you can see that 2 is inside this ideal, right? Because 1 is in here. Okay, so 2 is in here. 2 times 1 is in here. Not that, sometimes I don't distinguish between elements with coset, because when we talk about coset, right, we just really care about the representative. Okay, for example, Z mod and Z. There's only 0 up to n minus 1. Can we talk about n plus 1 or not? Can, right? Because n plus 1 is just 1. Yeah, so we equate the things inside the equivalent classes. Okay. So it's 2 inside the coset of 1 plus t squared minus 1 or not? My claim is no. How to say it? So my claim is 2 is not in here. So one intuitive way to see this, right, is what can you add to 1? You can just add multiple of t squared minus 1 to 1. Okay. So that means what? You always increase the degree of the polynomial. What can you multiply with? You can only multiply with multiple of t squared minus 1. Right. Question? A question? Yeah. My claim is 2 is not in here. Okay, how to show? So maybe try the contradiction. So suppose 2 is in 1 plus the ideal generated by t squared minus 1. This means what? This means 2 is equals to 1 plus some multiple of t squared minus 1. Okay? For some m inside my inside CT. Okay? Make sense? So what? So we will have 2 equals to 1 plus mt squared minus m. Okay? And then mt squared equals to, mt squared plus, should we use minus? Just use minus. So minus of m plus 1 is equals to 0. Yeah, no. But we know that t squared, all the monomials are linearly independent. Okay, so this means what? So since t squared and 1 are linearly independent, what's the definition of linearly independent? If you have what? So S1 up to Sn are linearly independent if there exists a linear dependency relation A1 x1 plus A2 x2 up to An xn equals to 0, all the Ai must be 0. So since t squared and 1 are linearly independent, we must have m equal to 0 and minus m plus 1 equals to 0. Which means what? Which means m equals 0 and m equals to minus 1, which is clearly false, because 0 not equals to minus 1. Okay. Okay, so 2 is not